Welcome. In this video, we are going to discuss about chi-square test for goodness of fit. Okay. Here, we have a set of observed values, okay, and we would like to know whether it can be assumed that the data is coming from a specific population. So, basically, here you may assume that we have a set of observed values. So when we say set of observed values, usually we denote them as these are some observations, okay, and we expect all these have come from some population p. This population maybe this population may be expected to have some distribution f of x, uh, or f of x. Okay, it can be a density or distribute a mass function, whatever. Okay, so all we like this may be the case, right? So we just want to compare an observed frequency with the corresponding values of an expected one. So these are the values that we have observed. Okay, correspondingly we will calculate some expected things. Okay, and we just check whether these are matching. We will make a hypothesis test whether they are from the expected population or they are the different. Okay, so this is what we will do. So assuming the specified distribution for the population, we find the expected value. So this expected value we will have to calculate. Okay, that one we denote it as e1 e1 e2 through en. And here the null hypothesis would be that the discrepancies between the observed and expected are insignificant, and of course the alternate is the negative statement of that of h naught. Okay, so here we make use of the chi-square statistic, that is observed minus expected whole square upon the expected thing. Okay, and here there are some notes. When we calculate chi-square, we expect the expected frequencies to be greater than or equal to 5. Suppose if it is smaller than 5, we just merge it with the neighboring class, okay, so that expected value is bigger than or equals 5. Okay, and k is the number of classes after any necessary merger. And here we expect, okay, after merging all these things we expect, we just count the total number of classes, that one we take it as k, and the degrees of freedom would be k minus 1, right? Okay, if some parameters are not known, then we have to estimate them from the sample data. So that is like if we have made any merger or like such thing happens, okay, if something are not known, then we'll have to estimate it from the sample data. In that case, how many estimations we have made, that one we take it as r, and the degrees of freedom would be k minus r minus 1, right? And alpha is the level of significance, and we will reject the null hypothesis if the calculated value is bigger than the table value. Okay, come back, let's get into the problems. A die was thrown 600 times. The frequencies of the phases are given below. Okay, so there are six phases, and 96 times one happened, 97 times two happened. Likewise, it is given, and the total is given to be 600. Okay, we'll have to test whether the die is unbiased or not, and we will use 5% level of significance. So the null hypothesis is that the die is unbiased against the die is biased at level of significance 0.05. And this one, how do we calculate? We know we expect the die to be unbiased. Okay, in that case, probability of x getting the value 1 is 1 upon 6, and probably it is not that x equals I is 1 upon 6 for all the I from 1 through 6. Therefore the expected value of getting I is the total number of times product with probability of x equals I, and this is nothing but 600 times of 1 upon 6, which is nothing but 100 for all the values of I, and that is why in the expected we have 100 for everything. Okay, Now that we just need to make the difference and square them and divide them by the expected one. So basically here we would have, if we just make the difference, it is 4, like be it minus 4 or plus 4, so it's square 16, here 9, 16, 9, 4 and 4, and the expected is 100 for everything. So if you just add all these things, it is 58 upon 100, isn't it? So which comes out to be 0.58. And for this level of significance, here we have not estimated anything from the, like, no observation is missing here. So we just estimate, therefore, okay, there is no point of estimating from the observe, like, from the data. So the degrees of freedom is 6 minus 1, which is 5. So chi square of from the table we have this one, and here this chi square is smaller than chi square alpha, so we will have to accept the null hypothesis, that is the die is unbiased. And moving to the next problem, we have a data relate to the number of aircraft accidents that occur during the various days of the interval for a given period of time. Test whether accidents are uniformly distributed over the week at 5% significance level. Okay, if you make the total of all these things, we get 30, 38, 50, 60, 74. If I'm not wrong, it is 84, isn't it? Yeah. So the total is 84. So there are 84 accidents in a week. It is said that it is uniformly distributed over the weeks. So on each day, we expect the same number of accidents to happen, and that is the expected frequency. Okay. Once we have the observed and expected, we can very well calculate the test statistic, and with this level of significance we can calculate the table value, and we note that chi square is smaller than chi square alpha, therefore we'll have to accept the null hypothesis that accidents are uniformly distributed over the week. Moving to the next problem. Here a theory predicts that the proportion of a beings in four groups, namely A, B, C and D, should be in this ratio, that is 9, 3, 3 and 1. In an experiment among 1600 beings, the numbers in the four groups are 882, 313, 287 and 118. This is the observed ones, right? Okay. Does the experiment support in theory? Okay. Now here the null hypothesis would be what? The beings are in the specified ratio, against that it is not. Okay. So now let us calculate. There are 1600. Okay, and we'll have to split this 1600 in this ratio. So it is 9 plus 3 plus 3 plus 1, which is 16. Okay, so 9 upon 16 times of 1600 is the first expected. 3 times of 16 upon 1600 is the second and third expected values. So 1 times of 16 upon 1600 is the last expected value. Now that we just calculate the test statistic, and from the table we read this value, and here also we see that chi square is less than chi square alpha, therefore we'll have to accept the null hypothesis that the experiment support the theory. Okay, moving to the next problem. Here it is said that a random sample of 60 printed books have been examined, and the number of defects are observed as follows. There are 32 books with 0 defects, 15 books with 1 defect, 9 books with 2 defect and 4 books with 3 defect, and the total is 60. Okay, we are asked to test whether the number of defects can be assumed to follow a Poisson distribution at this level of significance. Okay, so if supposing x is following a Poisson distribution, means this should have a parameter lambda, And what is this lambda with respect to the Poisson distribution? It is the mean, isn't it? Okay. Here, that can be estimated with this thing. So, summation, sum of all the frequencies times of x upon summation f. So, it is summation f cross x. So, you just multiply these two things, multiply these two things, multiply these two things, multiply these two things, add them up, and just sum the number of frequencies, that is 60. Okay. So, that gives us 0.75, right? So that is the parameter lambda. Therefore the Poisson distribution can be written as e to the power minus lambda product with lambda to the power x upon x factorial, where x can run from 0 onwards. Okay, now to find the expected frequencies for different values of x, we just make use of this one. Okay, so this e naught, we just substitute x equals 0 into it and calculate it as 28. And E1 we just substitute x equals 1 and calculate this one, and E2 we are doing the same. Okay, now that we have only four possibilities, 0, 1, 2 and 3. So 0, for 0, 1 and 2 we have calculated. For 3 we don't have to estimate it from here, because in total we have 60. So if we just subtract all the previous estimated things from the total 60, we would get E3 to be equal to 3, and that is how we get all these things. Okay, and if we notice here, the last class as smaller than 5, so this should be merged with the previous one. So when we merge it with the previous one, of course the observed also has to be merged, 13. Whereas in the data, we don't have any such thing. Okay, that is 0, 1 and 2 and 0, 1, 2 and 3 only we have. We just merged these two classes that was not given in the observed. So we are the one who are doing it. So this, okay, so from this what we get is k is 3, and we have, this is for the I, there are 0 defect, 1 0 defect, 1 defect, 2 defect and 3 defect. Now that we just combine these two things, 2 and 3, right? So there are 13 books with 2 and 3 defects, either 2 or 3 defects. So k equals 3 and r equals 1. Okay, now that we just take the difference and calculate the test statistic. Okay, for this level of significance, degrees of freedom is k minus r minus 1, which is 1. Okay, we just calculate this value and notice that chi square is smaller than the tabulated value. The calculated value is smaller than the tabulated value, therefore we'll have to accept h naught. Fine. And moving further, again we are asked to fit a Poisson distribution to the following data, and we are asked to test for its goodness of fit at this level. So x is given, f is given. Okay, we just estimate it. After estimating, we just calculate this one accordingly. Okay, that is how, using the fact that ei is the total 400 times of e to the power minus lambda, lambda to the power x upon x factorial. Since lambda value is 1, that does not have any effect. This is the thing that we have. Okay, we just substitute the value of x and estimate all these things. Okay, the last part we'll have to do as in the previous problem. Okay, again here this is smaller than 5, so we'll just merge it. Okay, after merging we see that there are 5 different cases and one was estimated. So this is the case. So 5 minus 1 minus 1, which is 3, is the degrees of freedom, and for this level of significance we just read this value from the table, and the test statistic gives us this value. Comparing these two things, we come to a conclusion that we are accepting the null hypothesis, that the fit is good, right? That's it. Thank you.